Hi friends, good morning. How are you? I hope you're doing great. Okay, let's start our virtual classroom. Uh, Today we'll study cryptographic hash functions. I'm sure you would have studied about hash function in the past, and the hash function that you have studied in data structure are slightly different from this hash function. So we'll study these and also look at details. So in this class, we'll cover the following things: introduction to cryptographic hash function, hash function motivation, that is why should we study hash function, details of the hash function, then one of the hash algorithms, which is tiger hash. Will not study this, I will leave it to you to study it from the book. Attacks on hash function, and finally some applications of the hash function. So we'll study one of the applications of the hash function, which is digital signature, in the next class. The contents of this presentation has been taken from two sources. The first is book by Mark Stamp, and second is book by Christopher Parr and Jan Peltz. So we will also use some of the notation that we have used earlier for symmetric key encryption and asymmetric key encryption. Symmetric key encryption, as you know, uses a shared secret key uh, between sender and receiver. The sender uses this key to encrypt the plain text P, and the output is encrypted text uh, called C. So C is equal to E, uh, and it has two parameters P and K. P is plain text and K is the key. When this message reaches the other end to the receiver uses the key K to decrypt it, and in turn what we get is nothing but plain text P. These two functions are shown here. In public key encryption, we use public key and private key. Private key is private with the sender. For example, if Alice is sending a message and she is encrypting the message with her private key, then she is not going to share the private key with anybody. She also generates one public key corresponding to her private key. So, and that she uses, that she shares with everybody else, and everybody else can use that key to decrypt the message that she has signed with or she has encrypted with her private key. Okay. The notations are as follows. If Alice is using the public key, her own public key, to encrypt a message, then we say M curly bracket subscript Alice. It means that Alice is using her public key to encrypt a message. Okay. Now, if Alice is using her private key to encrypt a message, which you call the signing a message, then it is shown as a square bracket M with subscript Alice. Okay. So if a message is encrypted with public key and then decrypted with private key, then we get the message M. Similarly, if message is encrypted with private key and decrypted with public key, then we also get message M. So this is the basic functionality. Okay. Now, as we discussed earlier, Alice will have her own private key, and also she will publish the public key, and that public key can be with anybody. However, Alice will only have her private key, okay, which she can use by herself. Okay, now let's look at few details of hash function. Hash is nothing but a digest of the message. So hash of a message is short and fixed in length. It means that whatever be the length of message, the output of hash function of that message is always short and fixed in size. Okay. For example, message could be of few megabits of size. The hash of that will be short. It means that it can be say 512 bytes, and it's a fix. It means that message length could be maybe 1 megabit or 2 megabit or 3 megabits. Or output is always fixed. Okay. So this is what we discuss is a just an example. Also, hash is nothing but a fingerprint of a message, which is a unique representation of a message. Okay. Another important property of hash function is that it does not use the keys. As we have seen in case of public key encryption and private key encryption, we use keys. Okay, hash function doesn't use any key. Input to hash function is nothing but hash function itself and the text that it wants to get hash of. Okay, so we use hash function essentially to get a signature or fingerprint of a message or a text. So generally we have large number of uses of hash function. Two commonly used functionality or usage of hash function is digital signature and hash max. We will study these two applications in the next class. Okay. Next we study is hash function. We can define hash function output as v, and hash function is h of m, where m is a message, h is hash function. M is of variable length, and z where z is fixed and small. Output of hash function is random. It means that for a small change in m, there is an unpredictable change in z. Okay, so we can see here how hash function works. Hash function is like a juicer. Okay, so whatever be the length of this message, output is always fixed. Okay, fixed in size, not in value. It means that if a message changes even by a bit, there is significant change in the output of Z. All right? Okay. Let's move to the next page. What are the desirable properties of hash function? As we discussed earlier, the length of the message that is to be hashed could be of any size. It means the message could be of any size, and when it's applied to hash, when to it we apply hash function, the output is always of fixed size. Okay. Secondly, which is very important property, that hash function should be computationally efficient. It means that it shouldn't take a lot of time to create output of a hash. Okay. Now this is significant advantage over encryption, especially symmetric key or private key encryption. Output of hash function should always be fixed length and independent of input length. So as we discussed this earlier, that output of hash function is always fixed for that particular hash function and is generally of 128 to 512 bits. And then the computed fingerprint should be highly sensitive to input bits. It means that if there is a small change in the input, then output should change significantly. Okay. All right. Now here, input output behavior of hash function is shown. Now the block here that's in the middle shows the hash function. Now let's give to this hash function input, which reads like Alice was beginning to get very tired of sitting in by her sister on the bank and having nothing to do. Okay, if we apply this input to hash function, then output is shown here. Now let's give input to this hash function something that reads like I am not a cook. Okay, the output of this hash function is FB93E283. Now, if we change this by a character and then input becomes I am not a cook, then output of the hash function is significantly different from earlier hash output, which is A3F4439B. Alright. So it means that with a single bit of change in input, there must be significant change in output of hash function. Okay, got it? Alright. So let's move to the next slide. What is the motivation for having hash function? Why can't we do the functionality of this using encryption and decryption? Again, let's look at an example. Suppose M signs message M with her private key. Okay. It means that Alice sends M and S to Bob. Now, where S is nothing but uh, signature of, or what we say is that encryption, private key encryption of M. So Alice takes her private key and encrypts M, and that becomes S, and then Alice sends to Bob both M and S. Okay. All right. So what's the issue here? Nothing. All right. So Bob, when receives this pair, that is M and S, then he applies public key of Alice, which he knows, and then creates message M. Or create the message, which if output of this is equal to M, then Bob knows that message has come from Alice. Right? Now the question is, can Alice just send S? What should be the answer? No. Why? Think about it. Okay. So what is the issue here? Why can't we use public key encryption method instead of hash function? Because we can send a message which is encoded with private key, and recipient will decode it with public key. We will know that it has come only from the sender. Now, the answer of this is that if M is big, then encryption of that with private key is also big, right? So it means that this first thing is this expensive to compute and send because they're long in length, and also it takes time to compute the encryption. Okay. Now instead of that, what is the length of message M? Alice first gets hash of that, which is small in size. Okay, which is a fingerprint of M, and then Alice sends M and S to Bob, where S is nothing but privately encrypted version of hash of M. Right. So Alice takes her private key and applies it to H and M, and that becomes signature. So Alice sends M and S to Bob. Bob has public key of Alice. So what Bob does is that he takes S and applies to S public key of Alice, and if this matches hash function of M, because he knows the hash function as well, then he knows that message has come from Alice. Alright. Where note that H is a public function, right? So it means that Bob knows H, and also Bob knows the public key of Alice. So to repeat, Alice creates a message M and signs it with hash. So she creates hash of H of M, okay, and then she computes the signature S with using by encrypting H of M with her private key. Okay, so she takes H of M and it privately encrypts this with key her private key. Okay, Alice then sends M and S to Bob, and Bob verifies HM by applying public key of Alice. Alright, so Bob knows M because he received it from Alice, and then Bob also knows H, so he applies H of M, and whatever is the output, if that matches with signature S that he has received from Alice, and when he applies to that public key of Alice. Okay, if H of M matches with uh, decrypted value of S, then he knows that message has come from Alice and it and it's authentic. Okay. Next is what properties must HFM satisfy? Okay. If true D, which is a bad guy, finds M dash, so that H of M is equal to H of M dash, then what Tudu can do is that if he is a man in the middle, then he can replace M and S, which Alice sends to Bob, with M dash and S. So when Bob receives M dash and S, he will never come to know that the M dash and S has come from Trudy instead of Alice. Okay. Can Bob detect this sampling? No, because H of M dash is equal to H of M, which is equivalent to uh, public key encrypted value of S. Okay. It means that when Bob receives message M and S, which that has come from Trudy, then he applies public key of Alice and they gets the value, and if it matches with H of M, which is equivalent to H of M dash, it means that he will never come to know whether he has received incorrect value of M. Ideally it should have been M, but he has received M dash, which is a fake version that comes from Trudy. Okay. Okay, let's move to the next thing, that is hash function details. Okay, so what are the properties of crypto hash function? First is compression. The output should be small. Second is efficiency. It should be very simple to compute h of x, where x is any input. Then very important property of this is one-wayness or pre-image resistance. Okay. So what is pre-image resistance? Says that given a value y, it is infeasible to find an x which is such that h of x is equivalent to y. What does it mean? It means that given one in hashed value is after applying a hash function, we get a hash value. Given a hash value y, now 2D gets say some value y, which is hash value. Can he find out the original text x? Okay. Now, this property says that given if somebody received hash value, then it is infeasible for that person to get the plain text x. All right. So, as an example, we store passwords as a hash value of the password. Okay. If somebody, say system admin guy, gets hash value of somebody's password, can system administrator from that hash value find out what is the password of a person? Okay. Now we can say that if ideally the hash function should be strong enough such that given hash value, no one should be able to find out the plain text or input text X. Okay. Second important property is second pre-image, or it's called weak collision resistance. Okay. Now it reads something like this. Given X and HX, it's infeasible to find out Y that is not equal to X such that H of Y is equal to H of X. What does this mean? Think. Okay. Given some value X, it means given some plain text or some string input and its hash output or hash value of that function, that input. Okay. Given that pair, it means that given the plain text and hash version of that text, it's impossible to find any other input Y such that H of Y is equal to H of X. Okay. So it means that given some text X, it could be of any length, and we know its hash value. Okay. So given both text and its hash value, it is not possible for any intruder or anybody to find out another text which will hash into same output. All right. Good. Now the next thing, which is strong collision resistance, or we call it simply collision resistance. Now it says that for any pair X and Y, which is nothing but input text, right? For two plain text, say X and Y, such that X is not equal to Y, its hash value should not be same. So it means that it's infeasible for somebody to find out two text or two inputs such that both will hash into same output value. Repeat. Okay. If I give you some hashed output, say hashed output of some password, okay, is it possible to find out two plain text passwords which hash into same output? Okay. So ideally, this should not be the case. It means that given one hash output, it should be infeasible for somebody to find out two inputs which will hash into same output. All right. Now, lot of collision might exist. It means that hash of X may be equal to hash of Y, but it should be very hard to find any. That's a property. All right. In case you have any question, please let me know offline through email or just make a phone call. Okay. Now let's look at some analogy. How large should be n before probability of someone has same birthday as me greater than half? We can easily solve this problem, right? So say I have my birthday is on say 1st January. Okay, the probability that you, say one of you, will not have birthday on 1st January is 364 by 365. The probability of a second person in the class also does not have birthday on 1st January is again 364 by 365. Okay, so if you solve this, if there are n number people, then we can say that 1 by 2 is equal to 1 minus 364 by 365 is for n, and if you solve this, you will get n is equal to 253. Fine, it's very simple mathematics. Okay, all right. Now the next question is that how many people must be in a room before probability is greater than half that two people have same birthday? How many people should be in room such that probability is greater than half that any two or more have the same birthday? In order to have probability greater than half, the number of people in the room should be approximately 253. It says that if probability is greater than half such that any two people or two or more people have same birthday, right? Then how many people do we really need in the class? So what should be the answer here approximately? The answer is 23. Okay, okay, good. Is it surprising or is it a paradox? May not be. The question is that why we are studying birthday here? Okay, can we have analogy? Okay, here it is. So hash function output, say h of x is of n bits. It means that it will have 2 raised power n different values. Okay. Say if n is of 64 bits, then there will be 2 raised power 64 different values. So if you hash about square root of 2 raised power n, which is 2 raised power n by 2 values, then you expect to find a collision. Okay. So earlier we have seen that if n is 23, which is approximately in the same order of square root of 365, then you get a collision. Okay, it means that two people will have birthday with probability greater than half. Okay, so here we can see that if you want to break a hash function, then which is of capital N bit long, then it will require 2 raised power n by 2 steps of work to break. Okay. All right. So it means that if you increase the value of n, then it becomes extremely hard for somebody to break it. Okay. Now let's look at two simple hash functions and see whether we can use it for crypto or not. Okay. Take x as a sequence of number, which is x1, x2, x3 up to xn, where xi is a byte. Okay, so essentially it is n byte long. Okay, then we've defined h of x is x1 plus x2 plus x3 up to xn with mod 256. Okay, just simply add them up and then do mod of 256. The question is that is it secure cryptographic hash? So take example two numbers or 2 bytes, which is 10101010, and second one is 00001111. H of x is nothing but just addition of these two. From this h of x, can we get two numbers which are different from x, that is uh, these two numbers given in original x? Okay. Now we can say that yes, it's very simple to find it out, but simple tricks, right? Simple mathematics. That if, for example, if y is 0, 0, 0, 0, 1, 1, 1, 1, and 1, 0, 1, 0, 1, 0, 1, 0, then h of x is equal to h of y. Okay. So if hash function is so simple as it's given here, then we cannot use it for cryptography. All right. Let's take up another example. If x we defined as a sequence of following bytes x0, x1, x2 up to xn minus 1, and we define hash as follows: h of x is equal to n to x1 plus n minus 1 into x2 and so on, mod 256. Then can we say this is secure cryptographic hash? Okay. Now similarly we can show it here that the hash of 0000, 0001 and 00001111 is same a hash of another sequence which is 00000000 and 00010001. So it means that although it looks complex, but this hash function is not secure. Okay. However, this hash function is still being used in many applications. Say rsync is one such application. Now, various applications require hash function with different properties. Okay, so we have seen three kinds of hash function properties. One is pre-image resistance, then second pre-image resistance, and third is collision resistance. And we can say that one-way password should have pre-image resistance property. Now, if you want to use hash function for intrusion prevention or detection, then hash function should have second pre-image resistance. Now, if you want to use hash function for digital signature, then hash function should have all three. That is a pre-image resistance, second pre-image resistance, and collision resistance. Now, question I want to ask you is why? Why, for example, for hash and digital signature, we need pre-image resistance, second pre-image resistance, and collision resistance. So what kind of attacks an attacker can have such that we need all three kind of resistances? Think about it. If you don't get answered, then look at the link given here to find out answers. All right. Okay. Okay. Now, if you are a hash function designer, the question is that how do you design hash function? Is it simple task? I guess it's extremely difficult task. It's a big research topic, and most of us shouldn't attempt to do that until we are really getting deep into hash function and do research for years. Okay. All right. So it means that we are in general going to be user of hash function rather than designer of hash function. However, we should know the important property. The important property of hash function is avalanche effect. Okay, what is avalanche effect? So here avalanche effect says that if you change one bit of input, it should affect at least half of the output bits. Okay, why do we need such a property? Because we want output of hash function to be as random as possible. Okay, such that nobody should be able to guess it. Okay, so let's assume that if you change one bit in the input and output is almost the same, then one can easily apply the reverse function and get the different string which hashes out to same output. Okay, When we create hash function or when we implement hash function, then we use messages in blocks of fixed size. Okay, uh, we'll look this property later. And then hash function calculation consists of certain number of rounds. It's not easy to design a hash function. Okay, what are different popular hash functions? There hash functions which are popular are MD5, SHA-1, SHA-256, SHA-384, SHA-512, and many others. Okay, MD5 was most popular. Okay, it was invented by Rivest. Output of MD5 is 128-bit. It's used heavily into internet. However, it's not very secure because MD5 collisions are easy to find. So we can say it's broken. Second one, which is quite popular, which has been standardized by US government is SHA-1. Okay, it has 160-bit output. The collision resistance is of course 2 raised power 80. Okay, people have found out that collisions are not extremely difficult to find. And more stronger hash functions are SHA-256 and SHA-384 and SHA-512, which respectively uses 256, 384, and 512 bits. Uh, these SHA-256, 384, and 512 are very difficult to break. Okay, let's move. Now this table shows the comparison of various hash functions, and we see that these four hashes, this SHA-254, SHA-256, 384, and 512, collisions have not found as yet. All right. Okay, please look at it carefully. Okay. Okay. There are various hash functions we have discussed earlier, like MD5, SHA-1, SHA-224, up to SHA-512. Uh, okay, so one design that people have discussed in general and recently been designed is Tiger Hash. Now we are not going to study this in detail. If you are interested, please refer book or any research paper. Uh, it's of course fast and strong. Is designed by Anderson. Ross Anderson is a famous cryptologician. Uh, he's written a famous book on cryptography. It's available online. Like MD5 and SHA-1, input is divided into 512-bit blocks. It means that whatever be length L of the text that is to be hashed is divided into 512-bit blocks, right? If in case the original message or original text is not multiple of 512, then it is padded, and then it's broken into 512-bit blocks. Okay. The output is the hash function output is 192 bits. Okay. And there are multiple rounds uh, by which we make the output. It means that between input and output, there are number of rounds the algorithm goes through, right? So input is x, which consists of x0, x1, up to xnn minus 1, and each xi is 512 bits. And then this is xi is input, right? In the phase 1, in the beginning, when the algorithm starts, we take three constants ABC and value of x0, and from that we get w, and from that goes input into some function, some calculation, and output of that is then shuffled, goes to next stage, and then this value of W with some change comes to this place, and some calculation happens, and then output goes here, and then some value of original W comes here and is applied to the function here, that's F9. And then there is a multiple rounds of this functionality. And then finally we get the output as some output at the bottom, which we have shown as ABC. Okay. So one round consists of some calculations, which is shown in the slide here. Okay. All right. So essentially, brute force method works, but if the value of n is large, then it is extremely difficult to break the hash function. Okay. Okay. Here we take m is the length of the hash value, or okay, hash value which is output of a hash function. So for p-wise resistance, we need to have 2 raised power m steps to break the hash function. For second p-image resistance hash function, we again need 2 raised power m steps to break it. For collision resistance, we need 2 raised power m by 2 steps to break it. Okay. So what does it mean? If you want to attack on pre-image resistance, say, so it means that given value of z equal to hx, okay, we know that output of a hash function which is z, we don't know x, and we need to find out x. Okay, so what we can do is that we can take some value of x at a random and compute h of x, and if matches with z, then obviously we have broken the hash function. The complexity of this is 2 raised power m. Okay. Second pre-image resistance is, if you know z equal to hx, okay, then for a given x, compute z, then find out y such that h of y is equal to z. Okay. Okay, it means that for given x and z, okay, we need to find out y such that h of y is equal to z. Okay, so it means that given one plain text and its hash value, which is z, then you just need to find out another text which hashes into same output value z. The complexity of this again is order 2 raised power m. Third is, of course, find out a pair x and y such that h of x is equal to h of y. This method is of course based on birthday paradox, and complexity is 2 raised power m by 2. Okay? So it means that this will require lesser number of steps than in case of pre-image and second pre-image resistance function. There are large number of applications of hash functions, like we use it for message authentication, message integrity, digital signatures, storing of password hashes, message fingerprint, and many other uses. Right. So we have already studied the storing of hash passwords in the past. Okay. Uh, the next class will study digital signatures, and later on we will also study how we can authenticate any message. Okay. Okay. To summarize, hash functions are keyless. We don't use keys as we use in case of public key and private key cryptography. Important properties of hash functions are pre-image resistance, that is one-wayness, weak collision, that is second pre-image, and strong collision, which is collision resistance. Hash function of length 256 keys are more desirable for long-term security. MD5 and SHA-1, uh, these are very popular, but uh, is easy to find out collisions in that. SHA-2 algorithm appears to be secure. Okay, and we have seen that hash function can be used for many applications, which includes message authentication and digital signature. All right. So thank you. In case you have any question, please ask me in the class or send an email or please make a phone call. Thank you. Take care of yourself. Bye.